Hello, and welcome to our notes on plate tectonics and all of the evidence that we've been looking at the whole unit and putting it all together and seeing how it all works together. Remember, you can pause and rewind, go back and rewatch these notes as many times as you need. Remember, the quiz at the end of the unit will be on these notes, so please pay special attention to what's in here. Now, we're actually going to start with a little review, which you don't have to copy because you already have it in your notes from our second notes on continental drift. But remember Alfred Wegener, and he proposed his theory of continental drift in 1911, and he got a bunch of different information and used his evidence. If you remember, he had four pieces of evidence, right? The fit of the continents, the fossil evidence, the ancient mountain ranges, and the past climate evidence or paleoclimatic evidence. And you will remember that the scientists of the time, they liked his evidence. And they said it was compelling and it was believable. But they thought, well, why don't we feel any movement? Why wouldn't there be any evidence to show that they were still moving? He wasn't even actually a scientist of geology. He was a meteorologist, which is basically like a weatherman. And so his theory really was very well accepted until after he died. Remember, he died on that expedition to Greenland collecting ice samples, trying to get more and more and more evidence because he really wanted everybody to believe his ideas. So that's kind of our review of where we started with the theory of continental drift. And again, the big reason why they didn't accept it, was because there was no mechanism for how it moved. He couldn't say how it worked. And then came this guy named Henry Hess. In 1963, he made a discovery that would basically prove that Wegener had been correct all along. And his theory was called the theory of seafloor spreading. So he used some new technology, which was radar, and he discovered that the seafloor has both trenches and mid-ocean ridges. Now, we talked about those in our plate boundary notes, but let's look at how they discovered it. He proposed that this seafloor spreading theory, and here's what he said. He said that hot, less dense material below the Earth's crust rose up toward the surface at these mid-ocean ridges and then flowed sideways. And that pushing out, that flowing down, actually pushed the seafloor away from the ridge in both directions. So if we see in this first little thing, we've got the molten magma coming up, and it's pushing both directions, and it's actually moving these plates away from each other. And so that's what his theory was. He said it spread apart at the mid-ocean ridge. That's why he called it seafloor spreading. And he said new seafloor was created, and that the older seafloor moved away from the ridge in opposite directions. And this helped explain how the crust could move, and something that the continental drift hypothesis couldn't do. Now, we looked at this in our last notes, in our plate boundary notes, and we now know this as a divergent plate boundary. But when Henry Hess thought of it and proposed this theory, it was still just a guess at his point. So Henry Hess explored the ocean basins, and he looked at a bunch of different things. They looked at seafloor features, like the trenches, like the mid-oceanic ridges. They also looked at the composition of the seafloor. So what was it actually made of? They looked at the age of the seafloor and seismicity, basically the seismic activity, and the paleomagnetic pattern that's produced on the seafloor. So let's talk about those in order here. First of all, I said he used radar. And when you use radar underneath the water, you actually call it sonar. So this word here, sonar, means radar that's underneath the ocean. So they basically took a boat, and they had this acoustic source, basically the thing that would send out the radar waves, which is sound waves, and they bounce these sound waves off of the ground of the sea floor, and as they would catch them, which was called the hydrophone array. Basically, it was a way to catch the sound waves or radar waves back. So radar can be used with just light waves or with sound waves, and underwater sound waves, we call them sonar. Now, here's a bunch of evidence they got for seafloor spreading. There was evidence that was done on a ship called the Glomar Challenger in 1968, and they started looking at the rocks of the seafloor. So they actually drilled down and took samples from the rocks. And they found that the youngest rocks were located near the mid-oceanic ridges. Let me go back for a second. This sonar really was a way to map the seafloor. So that was how we found out the seafloor features. This first one is by the sonar of the floor. And the composition they did at the Glomar Challenger, when they got information about the rocks, they saw that almost all of the rocks in the ocean were basalt. And we now know that all oceanic crust is primarily basalt rock. And like I said, they found that the youngest rocks were located at the mid-Atlantic ridges. So if we look at this picture here, it's kind of difficult to see. This is Africa, and this is Europe and Asia and Australia. Here's North America and South America. And this right here in between, this is the Pacific Ocean. And right here is the ocean between Africa and Australia. And here on this side is the Atlantic Ocean. And the red here down the line, every time you see this black line, that's a mid-oceanic ridge. And what you can see is the earliest rock is the red rock here, closest to the ridge. And then yellow is a little older, and yellow is older still, and blue is very old, and purple is really old. Now, the oldest rocks we found in the ocean are only 180 million years old. And they get progressively older the further away you get from the Earth. So youngest next to the ridge, and older as you get away. And not only do they get older as you get away, but they also are identical on either side. So you can see that it's coming out in the middle, and it's spreading on both sides evenly at the same rate. And so this kind of shows that, yes, new lithosphere is being created at the ridges, and it is spreading away both directions. Exactly what Henry Hess was trying to say. He then looked at all the earthquake information he had, and he said, whoa, earthquakes are concentrated at all of these places where we have these oceanic ridges and trenches. And basically now we know these as plate boundaries. And we can just look, every single one of these little circles is a earthquake. And they are so very, very concentrated along the ridges, or along the plate boundaries. So we got like the Scotia plate and the Cocos plate and the Caribbean plate and the Pacific plate here and the African plate, and they're perfectly outlined. It's actually one of the best ways we know where the plate boundaries are. Now here's the last and maybe most important one that really is a very interesting topic, and it's kind of a little difficult to understand sometimes, so we're going to go try and build you up from bottom to top. The Earth has a magnetic field. We believe it is because of our liquid outer core and that it's spinning, and because of the convection in the mantle and the spinning liquid outer core, that we actually have a magnetic field. And it's important. It helps us actually, protects our planet against solar flares and things like that we'll talk about in the astronomy unit. But what we've seen is that it acts like a big bar magnet. So here's our North Pole, and what we've seen is that if you were to put a magnet around the Earth, that the magnet tips would actually switch around and change depending on its location. So the Earth's magnetic field affects all the magnetic objects on Earth. Now, what we found is that when rocks cool on the Earth's surface, they record Earth's magnetic field. So basically, all the little molecules inside the rock line up so that it is in the same direction as our magnetic field. And when we go back through layers and layers of Earth, what we find is that that magnetic field has changed. That up to about 500,000 years ago, it went in the same direction it's going now. But before then, it had actually been reversed. So this North Pole was actually going the other direction, and the South Pole was going this way. It somehow flip-flops, and what we found is going back layer through layer through layer through layer through layer, is that the magnetic, the direction of the Earth's magnetic field actually keeps flip-flopping back and forth, back and forth, back and forth. I honestly can't tell you why. I don't know. Maybe we can look it up and see if we can figure out the answer. But I know that it happens, and I know that the rocks record the that movement, that change, because every time a rock is formed, as magma comes up from the mantle and it cools down, it aligns itself with the magnetic field of the Earth. So what paleomagnetism means is, paleo again means really old, and magnetism means the magnetic field. We're looking at all the different old magnetic fields by looking at all the rocks, and what it shows is that they alternate stripes of normal versus reverse polarity at the oceanic ridges. And so if we look at our seafloor spreading again, we notice normal magnetism, and then reverse magnetism, and then normal magnetism, and then reverse magnetism. So if we look at this over time, we actually can see the Earth spreading apart and the strips of magnetism flipping back and forth. So Henry Hess, he looked at all this info and he envisioned this new seafloor being created, the mid-oceanic ridge. So we have the newest towards the oceanic ridge and older as we get farther out, and that the magnetism flip-flops back and forth. And he theorized that as it got to the trenches, where the two different plates met, that we'd get subduction and that it would be destroyed. Now, from that led to convection, which we talked about before, of how it works. And this was kind of the driving force behind his seafloor spreading theory, that we have the convection cells within the mantle, and they're pushing at the mid-oceanic ridges, and they're pulling down over at the subduction zones. And so what we've basically got is we take Hess's discovery of seafloor spreading and Wegener's continental drift theory combined, and we now call that the theory of plate tectonics, or the plate tectonic theory. And all that says is the Earth's crust and part of the upper mantle are broken into sections called plates, which move on a plastic-like layer of the mantle. So everything we've been doing for this whole unit comes down to this moment where we have the theory of plate tectonics, where we know there are plates, where we know they move, where we know there are 3 different types of plate boundaries, that we're taking that original idea from Wegener of continental drift, and we're combining it with the new discoveries from Hess to make this whole theory come together. And now, essentially, every scientist alive accepts this theory and agrees with it, and we can now even track the movement of the plates. And of course, we track all of the earthquakes and everything. So it took a lot of work from a lot of different people to put this theory together. But we now know the theory of plate tectonics is a true thing, and that is all of our evidence to combine to make it one unified theory. This is our last notes of our unit, and I hope you feel like this tied everything else together for you. We will put all of our notes together for our final test, and I will see you in class.